Now, in this session, we are going to see the QFET assumptions and Fermi level. What is QFET? QFET stands for Quantum Free Electron Theory. What are the assumptions? In the previous sessions, we have seen the failures of CFET. So, in order to overcome the failures, another theory was given as Quantum Free Electron Theory, and there are some assumptions. This quantum free electron theory was given by Sommerfeld, and here QFET was successfully explained all the drawbacks of CFET, that is classical free electron theory. What are the assumptions? We are going to see. What are the assumptions of QFET? The energy values of conduction electrons are quantized. The allowed energy values are realized in terms of set of energy values. So this is the assumptions which led to many changes, and because of this first assumptions, this QFET could successfully explain the failures of CFET. Therefore, this QFET was a big success. Now, the second assumption is the distribution of electrons in the various allowed energy levels occurs as per the Pauli's exclusion principle and also obey Fermi-Dirac quantum statistics. You have studied in your lower classes what is Pauli's exclusion principle, which states that no two electrons will have the same set of all four quantum numbers. And this Pauli's exclusion principle will be obeyed by the electrons, and these electrons are obeying the Fermi-Dirac quantum statistics. So, what is Fermi-Dirac statistics? Fermi-Dirac quantum statistics means the one which obey Pauli's exclusion principle will obey Fermi-Dirac, will follow Fermi-Dirac quantum statistics. Here, electron is obeying the Pauli's exclusion principle. Therefore, electron falls under Fermi-Dirac quantum statistics, or electrons has to obey Fermi-Dirac statistics. Next is the free electrons travel in a constant potential inside the metal but stay confined within the boundaries. The fourth assumption is the attraction between the free electrons and the lattice ions and the repulsion between the electrons themselves are ignored. So these are the four assumptions. In this, majorly the changed ones are 1 and 2, 3 and 4 are the same as that of the CFET assumptions. The only two are the energy values of electrons are quantized. This is a major change which led to the success of QFET. Because of these two changes, it could successfully explain all the characteristics of electrons and how the conductivity is happening, and all the experimental results are in agreement with the theoretical. Therefore, it's a big success. The first two assumptions are very, very important, which led to the success of the QFET. Next is density of states. This has come into picture because the energy states of electrons are quantized. Quantized means fixed, defined. Now, density of state. It is defined as a number of available state per unit energy range centered at a given energy E in a valence band of material of unit volume. It is denoted by G of E. That means the density of state is denoted by G of E. The product G of E into dE gives the number of states in the energy interval dE plus dE at E. That is the product of GE and dE. GE is nothing but the density of states, and dE gives the number of states in the energy interval dE at E. GE represents the density of states at E. GE, that is density of state, represents the GE is nothing but a density of state, represents the density of state at E. That means GE dE is nothing but it is the number of states in the energy interval dE at E. As dE is small, a small infinitesimal, either plus or minus, as dE is small, it is assumed that GE is constant between E and E plus dE. The density of states in the range E and E plus dE is denoted by GE dE. If you look at the diagram here, it could be understood in a better way. Here, E1 is the ground state and E2 is the higher energy state, and dE is a small value of dE. dE is a small value between E1 and E2. That means whatever the sentences that were explained here, the product GE dE gives a number of states in the energy interval dE at E. The density of states in the range E and E plus dE. That means we are going to see the density of states between E. That is E and E plus dE is denoted by GE dE. Is given by 8 root 2 pi m to the power of 3 by 2 by h cube e to the power of 1 by 2 dE. This is the density of states. Next we start with the Fermi-Dirac statistics. What are Fermi-Dirac statistics? Under thermal equilibrium, the free electrons acquire energy obeying the statistical rule known as Fermi-Dirac statistics. Fermi-Dirac statistics is applicable to assembly of particles which obey Pauli's exclusion principle. As I told you before, in the assumptions of QFET, I have mentioned the particles which obey Pauli's exclusion principle has to obey Fermi-Dirac statistics, or fermions are taken to be followed Fermi-Dirac statistics. So, Fermi-Dirac statistics is applicable to assembly of particles which obey Pauli's exclusion principle. They must also be identical particles of spin 1 by 2 and are indistinguishable. As electrons satisfies these conditions, they obey Fermi-Dirac statistics. We know that electrons obey Pauli's exclusion principles and they must be identical particles of spin 1 by 2 and are indistinguishable. Therefore, all these conditions are satisfied by electrons. Therefore, electrons obey Fermi-Dirac statistics. Fermi-Dirac statistics permits evaluation of probability of finding an electron occupying energy levels in certain energy range through a function called Fermi factor denoted by f of E. According to this theory, the free electrons are quantum particles. The distribution of electrons amongst various energy levels is in accordance with the Pauli's exclusion principle. The number of conduction electrons per unit range per unit volume is given by Ne dE, which is nothing but GE dE dot f of E. F of E is nothing but a Fermi factor and GE dE is nothing but the density of states, which we have seen in the previous slide. Now we will see what is a Fermi energy. The energy corresponding to highest occupied energy level at 0 degree absolute is called as Fermi energy, and the energy level is referred to as a Fermi level. It is denoted by EF. What exactly is the Fermi energy? The energy corresponding to highest occupied level at 0 degree absolute. If you look at the figure here, see, you can see the electrons, the lowest level is completely filled as you come up to 2 electrons in each orbit at a particular temperature T equals to 0 Kelvin. The vacant energy levels, you can see the diagram. Now, if you see at T equals to 0, what is the highest occupied energy level? That level is called as a Fermi energy level. The energy corresponding to highest occupied level at 0 degree absolute is called as Fermi energy, and the energy level is referred as Fermi level. This is denoted by EF. The highest occupied level is Fermi energy, and the energy level is referred as Fermi energy level. EF is equal to h square by 8m into 3n by pi whole to the power of 2 by 3. EF is denoted by Fermi level. Expression for Fermi energy. According to Fermi-Dirac theory, the total number of conduction electrons per unit range per unit volume is given by Ne is equal to integral of 0 to infinity GE dE dot f of E is equal to 0 to integral of 0 to infinity 8 root 2 pi m per 3 by 2 by h cube e to the power of 1 by 2 dE dot 1. This value of GE we have done in the previous slide. GE value is being given. F of E is 1. Therefore, at 0 Kelvin, the top of the electron energy distribution is defined as EF. We know that EF is the highest occupied energy level at T equals to 0 temperature. So, the integral becomes 0 to EF. And if you take the value of N can be written as 8 root 2 pi m to the power of 3 by 2 by h cube. Since this is a constant value, it comes out of the integral. And as per the condition mentioned over there, so integral becomes 0 to EF. E to the power of 1 by 2 dE. Substituting the terms, all this and rearranging, that is, if you substitute, evaluate all the things and rearranging the terms, you will be getting EF is equal to h square by 8m into 3n by pi whole to the power of 2 by 3. This is the expression for Fermi energy. Next is a Fermi temperature. It is a temperature at which average thermal energy of a free electron in a solid becomes equal to Fermi energy at 0 Kelvin. It is denoted by TF. Fermi temperature, it is average thermal energy of a free electron in a solid becomes equal to Fermi energy. So TF is equal to EF by K, where K is a Boltzmann constant. Next is a Fermi velocity. The velocity of an electron which occupy the Fermi level is called as a Fermi velocity. Therefore, Vf is equal to 2Ef by m under root. So, the velocity of an electron which will occupy the Fermi level is called as a Fermi velocity. Next is expression for electrical conductivity in metals, QFET. Free electrons obey FD, Fermi Dirac statistics, by applying FD statistic. That is, sigma is equal to Ne square lambda by m star Vf, where m star is the effective mass of electron. So, these three definitions, or the Fermi temperature, Fermi velocity, are used to many of the numericals, and expression for electrical conductivity, which we are going to, based on this expression, we are going to see the success of QFET. This is the major revolution for the quantum free electron theory. Sigma is equal to Ne square lambda by m star Vf. With this equation, we are going to see the further QFET. Thank you.